Heterocyclic amines are, as we mentioned previously, compounds that are cyclic with at least one nitrogen involved. Pyrrole is an example of a heterocyclic amine. It has a nitrogen plus 4 carbons. It is an aromatic compound, as we have mentioned before. Each carbon has a p orbital with a single electron, and the nitrogen will have the lone pair in a p orbital that is aligned with the other p orbitals on the carbons, giving us 6 pi electrons, 4 from each, or 4 electrons from the carbons and then 2 from the nitrogen. Because there are 6 pi electrons, this compound is aromatic. Pyrrole reacts with different electrophiles in electrophilic aromatic substitution reactions. For example, if we mix it with Br2, we'll get a bromination at the second carbon of pyrrole. Now, this reaction actually occurs faster than benzene, since pyrrole is considered a more electron-rich aromatic ring, in part due to this nitrogen, which the lone pair can be donated as shown here. So the lone pair will push electron density this way, the double bond will move this way, and that means that these electrons will be able to attack an electrophile and add it to the second position of the ring. Electrophilic aromatic substitution reactions with pyrroles typically occur at the second carbon rather than the third carbon of the pyrrole ring. The pyrrole ring is symmetrical, so this carbon is the same as that one, and this carbon is the same as that one. If we do a nitration, for example, of pyrrole, the nitro group will add to this carbon, in part because the lone pair is pushing electron density towards this carbon. So the lone pair, if we move it here, will form a double bond. This double bond will move here to put a double bond here. And then this carbon will be used to attack the electrophile. Another way of viewing this is that if the substitution of whatever electrophile, in this case the nitro group, adds to the second carbon, we're going to have 3 resonance structures compared to only 2 resonance structures if the electrophile adds to the third carbon. For that reason, we're going to get primarily substitution at the second carbon. Many other heterocyclic amines are found in important biological molecules. For example, imidazole is found in the amino acid histidine, while thiazole is found in vitamin B1. Imidazole contains 2 nitrogens. One of those nitrogens is, at least its lone pair, is part of the aromatic ring of this molecule. As a result, the lone pair on this nitrogen is actually basic, while the lone pair on this nitrogen is not. Since if we use the lone pair on the nitrogen in position 1 to react with an acid, we would then break the aromaticity of imidazole. In this question, we want to draw the p orbitals of a molecule we just saw, which is thiazole. It is a 5-member ring with a sulfur, couple of double bonds, and a nitrogen here. Thiazole is a molecule that contains 3 carbons, 1 nitrogen, and 1 sulfur. The sulfur uses one of its lone pairs to complete the aromaticity of this compound. So we're going to put a lone pair on the sulfur in a p orbital. This carbon will have a double bond to this carbon, and so we're going to put a p orbital on each of these carbons with 1 electron in each. The nitrogen will have a p orbital with a single electron, since it's going to make a double bond to this carbon. And the carbon will also have a p orbital with a single electron. So overall, there are 2 electrons from these 2 atoms, 2 more electrons from this double bond here, and 2 more electrons from the lone pair on the sulfur, giving us 6 pi electrons for this compound to make it aromatic. The sulfur also has a p orbital, a lone pair in an sp2 orbital that would not be aligned with the pi cloud around this ring. The nitrogen will also have a lone pair that is also part of an sp2 orbital that will also be perpendicular to the pi cloud of this compound. As we covered in the aromatic chapter, pyridine is an aromatic compound that contains 5 carbons and 1 nitrogen. Each carbon will have a p orbital with a single electron, and the nitrogen will also have a p orbital with a single electron. That gives us 6 pi electrons for the pi cloud, and pyridine as a result is aromatic. The lone pair on pyridine is not necessary for pyridine to be aromatic, so the lone pair will be in an sp2 orbital away from the pi cloud. Note that the nitrogen in pyridine is typically less basic than a amine that is sp3 hybridized, so a typical alkyl amine. One explanation for this is that the nitrogen in pyridine is sp2 hybridized, which generally means that nitrogen is more electronegative. It holds on to the lone pair tighter compared to an sp3 nitrogen. Pyridine, similar to benzene, will undergo electrophilic aromatic substitution reactions. However, the reaction is generally very slow. In fact, in order to do a bromination reaction, we have to heat pyridine and bromine to 300 degrees just to get a 30% yield of 3-bromopyridine. Pyridine is considered an electron-poor aromatic ring compared to benzene, and Perot, as we mentioned before, is actually considered an electron-rich aromatic ring and reacts a lot faster than benzene and pyridine in electrophilic aromatic substitution reactions. Pyridine typically undergoes electrophilic aromatic substitution reactions at the 3rd carbon, which is this one here. The reason for this is once the electrophile adds, we get an intermediate that has 3 resonance structures where the positive charge is always on a carbon as seen here and here. If the electrophile adds to the 2nd carbon, which is this one, we'll have 3 resonance structures, 1 or 2 that have a positive charge on a carbon, but one of the resonance structures ends up with a positive charge on the more electronegative nitrogen atom, which makes this route less likely. The same thing occurs when the electrophile adds to the 4th carbon, which is this carbon. We obtain an intermediate with 2 resonance structures that have a positive charge on a carbon, as shown by these 2. But one of the resonance structures has a positive charge on the nitrogen, which again is an electronegative atom. We normally don't want to put a positive charge on electronegative atoms. So this route is also unfavorable, which means typically we see electrophiles adding to the 3rd carbon of pyridine. There are many important polycyclic heterocyclic amines, such as quinoline, isoquinoline, indole, and purine, that contain both a heterocyclic amine as well as multiple rings. Both quinoline and isoquinoline can also react in electrophilic aromatic substitution reactions similar to benzene. However, they tend to be less reactive than quinoline and isoquinoline. Similar to pyridine, quinoline and isoquinoline are considered electron-poor rings. As a result, the reaction is generally slow. Here's an example with quinoline and a bromination reaction, which leads to the bromine adding to the 5th carbon or the 8th carbon in roughly a 1-to-1 ratio. Generally, the benzene is slightly more electron-rich than the pyridine of quinoline. For that reason, we get substitution primarily at the benzene carbons, like position 5 and position 8. With isoquinoline, if we try to do a nitration, again, we're going to get primarily substitution on the benzene ring side of the molecule rather than the pyridine ring, which is less electron-rich than benzene. Indole is considered a aromatic ring that is more electron-rich overall than benzene. Specifically, the pyrrole part of the indole ring is more electron-rich. So substitution through electrophilic aromatic substitution usually occurs in that ring, specifically at position 3. The reason for this is the nitrogen will push electron density towards this carbon by forming a double bond here and using this double bond to attack the electrophile. That would lead us to substitution at the 3rd carbon. Purine has 3 basic pyridine-like nitrogens. Those would be the nitrogen at position 7, 1, and 3. These nitrogens can react with acid pretty freely. However, the nitrogen at position 9 is more like the nitrogen in indole and pyrrole, which are required to complete the aromaticity of the ring, in this case for indole, as well as for purine. And so that nitrogen lone pair is usually not very basic. Electrophilic aromatic substitution reactions with purine typically occurs at carbon 8 here of the ring. Many important biological molecules as well as pharmaceutical drugs contain heterocyclic amines within their structures. For example, quinine, which is an antimalarial drug, contains quinine. Tryptophan contains the tryptophan ring. Adenine, which is a DNA base, contains the purine ring. The same thing occurs in Viagra. We have a pyridine ring in this coenzyme shown here, and there are multiple pyrrole rings in the molecule heme. In this question, we want to figure out which of the 2 nitrogens in the following compound, which is NN-dimethyltryptamine, which is a hallucinogenic indole molecule, is more basic. We have the option of this nitrogen of the indole ring, as well as this nitrogen that is an alkyl amine. The lone pair on the nitrogen of this indole ring is required to complete the aromaticity of the indole ring, and therefore is typically not available to do reactions with acids or electrophiles. So this nitrogen is generally not considered a basic amine. The nitrogen here on this side group, however, is free to react with acids and electrophiles. So this is going to be the most basic nitrogen in this molecule.